Thank you for a kind invitation. So it's my great pleasure to visit a new interdisciplinary research institute. So I try to explain one of the topic in our community to the people in the other research field, and I hope to discuss with you at the end of the seminar. Because finally, I'd like to talk about some helicity or not linking of magnetic field created by hydrodynamic time evolutions. So actually, it's nice to meet you guys in different research field for the first time, and also some of my colleagues first time after the pandemic. So this is actually my first time to travel around Japan after the pandemic. So I moved to China during the pandemic, and now I'm in Zheijan University. So let me just briefly introduce Zheijan University because it's not really recognized by people in Japan. So Zheijan University is located in Hangzhou city that is actually very close to Shanghai. So if you take a first train, it takes just 1 hour from Shanghai. And it's a very beautiful place. I think it's one of the most beautiful places in China. And so the Hangzhou city has a big lake called Shifu, West Lake. So this is one of World Heritage. And Longjing is known as green tea leaves. So you can enjoy nice Chinese green tea here. So the original campus of Zhejiang University was very close to Lake District, but we moved to newer campus. It's a little bit far from Shifu, but it's just 10 kilometers away. So if you visit us, you can enjoy those historical places. So you are very welcome to visit Zhejiang University in your future. Okay, so moving to physics content, science content. So taking account that you come from a different research field, I try to first explain what is chirality in our sense in high energy physics community. And then I talk about also chiral anomaly. So I'll try to explain what chiral anomaly is in a very brief way. And then I move to also explain what hydrodynamics is as an effective field theory in physics. And finally, I move to the main topic that is chiral MagnetoHydrodynamics and its solutions, which exhibit some unstable modes. Okay, so first of all, what is chirality? So if we share the same background in physics, the definition is very simple. It's just the eigenvalue gamma 5, but I know you wouldn't understand what is gamma 5. And also this definition is even abstract for physicists. So we try to understand the meaning of chirality in a different way. So instead of chirality, we focus on spin. The spin is a quantized angular momentum that is intrinsic to the particles. So in classical mechanics, you have, if you have rotating motion, you have angular momentum. But this spin is nothing to do with the particle motion. Even the particle at rest have some angular momentum component, and it's also quantized. So this was a big surprise in early days of quantum mechanics, but the physicists accepted this because it is an experimental fact. So electrons are classified as a family of spin 1/2 fermions. You have also spin 0 and spin 1 and spin 3/2 particles and so on. But we focus on spin 1/2 particles. Okay, so this is just a quantized angular momentum. It is angular momentum. And the point is that the spin 1/2 particles can take only 2 states. which is usually referred to up state and down state. So if you want to completely classify or specify the state of particles, you need to specify spin as well as momentum. So momentum also appears in classical mechanics, but spin is purely quantum object. So you need to specify the spin to specify the quantum state of particles. So this is the first message in this slide. And the next, we consider helicity, something called helicity. And it is particularly interesting if you focus on the spin component along the momentum. The reason is the following. So if you have if you put mirror in front of particles, actually momentum and spin angular momentum have different property. The momentum perpendicular to the mirror is reflected if you look up the world inside mirror. So this is just mirror reflection, but spin angular momentum doesn't change the spin. Doesn't change the sign. The reason is that spin should share the same property as angular momentum. So in classical mechanics, the angular momentum is defined with the quantity, the coordinate, and the momentum parallel to the mirror. If you look up the component perpendicular to mirror, so it doesn't change the sign. So this implies if you look up the spin component projected to the momentum direction, you can classify the Fermion into the two types that has plus sign for helicity and minus sign for helicity. And we call this state as right-handed helicity because it's like the right-handed skew. And the other one is called left-handed helicity. And the reason why I'm talking about helicity is helicity agrees with chirality in some limit. So for clarity, I have to say they are different quantity for the first place, but they are similar quantities. So you can understand that, in this seminar, we try not to worry about details. So you can understand helicity is equal to chirality. They are similar things. Okay, so the second message is even elementary particles have notion of right-handed and left-handed particles, even without structures. So of course, if you look at some molecules, they can have right-handed or left-handed structures, depending on special structures. But even elementary particles have notion of R and L. So I will talk about this chirality in our community. So chirality is indeed important because if you look at the elementary theory for weak interaction that induces beta decay in nuclei, actually right-handed particle and left-handed particle behave differently in the weak theory. The most prominent outcome of chiral theory is that you have only discovered left-handed neutrinos. So all the neutrinos discovered in experiment is left-handed. So you haven't discovered right-handed neutrinos. So maybe, it's still a subject of active research. Nobody knows why right-handed is not discovered yet. But this at least implies that right and left particles behave differently in fundamental theory. And also, even in theories like electromagnetic interaction or strong interaction, the particles behave the same way, but we could have a different number of right-handed particles and left-handed particles. So in such case, again, the chirality could play an important role in the time of evolution of the system. So here I define something called chirality invariance or axial charge. That is the difference between number of right-handed particles and left-handed particles. So you understand if you change the parity or if you apply the mirror reflection, the sign of axial charge density changes sign. So this breaks parity. Okay, so now we discuss how the difference between right-handed particle and the left-handed particle could be created in the system. That is due to chiral anomaly. So this is very subtle property in quantum field theory. So it's very challenging to explain chiral anomaly in one slide. But again, we try not to worry about very details. So let's try to the basic idea with some schematic discussions. Okay, so chiral anomaly refers to non-conservation of axial charge. So if right-hand side were 0, this is just continuity equation, conservation equation. But those people, high energy guys, found that actually right-hand side is non-zero if you include quantum effect. So this non-conservation is referred to chiral anomaly. And why it's induced is discussed in the following way. Okay, so anyway, we need to apply electric field and magnetic field. So let's consider the case where you apply magnetic field. So then a charged particle start rotating. So this is cyclotron motion due to the Lorentz force. And as you increase the magnitude of magnetic field, the cyclotron radius shrinks to 0 to the infinitesimal radius. In that case, you can have only this particle can have only one-dimensional motion. So we consider this limit. So in this limit, the relation between energy and momentum is very simple. It's just linearly proportional to each other. So energy is equal to plus minus pz. The particle can move along B or anti-parallel to B. Okay, so this is a very simple relation. And further, you apply the electric field. So then you will get additional energy depending on time in this way. So if you draw a picture, it looks like this. So you have a particle in vacuum. Okay, I should mention that the energy origin is here. So the particle is occupied up to 0 energy in vacuum. But if you apply electric field, those negative energy state acquires energy and goes up in this way. So in this figure, you get 2 particles here. And if you examine the signs very carefully, it turns out you should also get antiparticle, 2 antiparticles here. Because in vacuum, you don't have any net electric charges. So even after applying electric field, you should have 0 net electric charge. So if you create 2 particles, you should create 2 antiparticles as well. So the total net charge, total charge is still 0, but you find some difference around here. So this is this gives rise to this non-conservation because this particle and the antiparticle contribute to the axial charge with opposite sign. So in this case, you have +4 axial charge. Okay, so but this is the very subtle point because anyway, you have infinite number of particles to the minus momentum and also this way. So you have initially infinite number of right-handed particles and left-handed particles. So this is the relativistic theory. And this is called Dirac C, which doesn't have bottoms. So this bottom continues to infinity. So the question is, what is the difference between infinities? So this is a very subtle question. And actually, if you compute it in some different ways, you will get a different answer. So you need to give some constraint. That is gauge invariance. So meaning that the total charge is still conserved, and also this result is given by physical quantity E and B. So in that case, you can get the unique result in this way. Okay. So if you apply E and B, you will get the different number of axial charge. That is chiral anomaly. So where does chiral invariance play a role? So as I already mentioned, weak interaction is inherently chiral. So if you go back to the early universe, you have electroweak era. In that case, you need to deal with chirality invariance. Then also, if you look at the supernovae, where the weak interaction play a role because the proton captures electron to become a neutron. That is a weak interaction. So the supernovae is also interesting application. And also, if you look at heavy ion collisions, after the collision, two nuclei are communicating with each other through electromagnetic field, but in QCD. So it has a color indices in this way. But anyway, you will get the E dot B. That induces chirality imbalance through the chiral anomaly that we discussed in the previous slide. And also in recent condensed matter system, the people created something called Dirac wire simulators. So so this is the energy band of Dirac and wire simulators. If you focus on this region, you have linear dispersion relations. It's just like this relation. So actually, Dirac simulators play an important role to discuss the chirality in physics. But actually, there's a difference because this is actually not the bottomless, but it is connected to some other cones in this way. So in that sense, there's no real anomaly, chiral anomaly in condensed matter system, but they can mimic the high energy physics. Okay, so we are going to move hydrodynamics, but if you have any questions about chirality in physics, maybe you can ask question at this moment. Okay, so if not,
can I ask
yeah,
a
sure.
quick question? So in the previous slide, you introduced electric field B, BE, and the magnetic field B. Are they static field or they can be dynamical?
They can be dynamical.
Can be dynamic.
Right. So this schematic discussion is only a particular case, but this relation hold for space and time dependent E and B, and also right. It doesn't have to be strong, basically.
Yeah. Thank you very much.
Okay, any other questions? Okay, so let's move to the second part. So I will try to introduce general aspects in hydrodynamics. So this is a very brief introduction. So in heavy ion collisions, we discovered hydrodynamic behavior of quark-gluon plasma. So that means that created plasma is not like a free streaming particles, but they interact with each other very strongly so that they exhibit some corrective behaviors. So without strong interaction, you are not able to see such a corrective behavior. So those two are extreme cases. So this is free streaming limit. This is hydrodynamic limit. And you can, of course, find the hydrodynamic behavior in some other systems. For example, in condensed matter system, you have hydrodynamic flow in graphene that is two-dimensional material. And also this is example of called a strange matter. Usually resistivity comes from impurity scattering this way. But in this particular materials, you find hydrodynamic behavior because of the frequent interaction among electrons. So those two are also two extreme cases. And also you can apply hydrodynamics to the astrophysics, like solar wind or supernovae. So actually, what is the common concept underlying in various systems? Why hydrodynamics works in universal way? So actually, hydrodynamics is universal low energy effective field theory. So if you goes to the low energy scale, the system usually behaves like hydrodynamics. The reason is the following. So you want to construct low energy effective theory. Therefore, you need to identify the relevant degrees of freedom that plays a role in some particular energy scale. That is gapless modes excited by infinitesimal energy. So that means that if you apply the small energy, you can create some excitations. Also, there are gap excitation, but you wouldn't excite those higher energy state by infinitesimal energy injection. So we can neglect those gap mode. We can only focus on gapless modes. And how you can identify gapless mode is the following. So in real space-time, gapless mode corresponds to conserved charges, because by definition, conserved charges survive for long time scale. So if you identify conserved charges, that plays a role of gapless mode. So the equation of motion is given by a set of conservation laws from Noether's theorem. So Noether's theorem states that if you have symmetry of the system, you have corresponding conservation laws. So for example, the simplest one is translational symmetry. So if there's no particular origin of the space-time, you have translational symmetry. And the consequence of translational symmetry is the energy momentum conservation. So this is not specific to quantum effect, but this is just a theorem in classical mechanics. So conservation law looks like this. So theta mu nu is energy momentum tensor. In the rest frame of fluid, it looks like this diagonal matrix. So where epsilon is energy density and P is pressure. So I stick to Lorentz covariant notation. Okay, so hydrodynamics is low energy effective field theory based on symmetries. So as long as you have the same symmetry in different systems, you have the same hydrodynamics. So in that sense, the hydrodynamics is universal theory. And later, we will include a magnetic field and chirality invariance. And we will try to construct the chiral magnetohydrodynamics. Okay, but this is not the end of the story, because the set of equations is not a closed system. So the good news is if you have some number of conserved charges, you have corresponding number of equations, the conservation equations. So it looks like a closed system, but actually not, because there's a special component of conserved current that has to be expressed with conserved charges. Okay, zeroth component is conserved charges, but special component is not. It's a current. So for example, we can go back to this slide. So suppose NA is conserved quantity, but still you have unknown vector JA. This is current. So we want to express this current by using NA, something like this. Okay, so that is called constitutive equation. Constitutive equation is a relation between spatial component and the temporal component. And you can use derivative expansion that works in the long space-time scale. Because in derivative, the coordinates and the time comes in the denominator. So the expansion with respect to derivative should work in long space-time scale. So the question is how we can get the coefficient Cn. So there are a few approaches to get the constitutive equations. The most fundamental one is to start with the fundamental theory, quantum field theory, kinetic theory, something like this. So they are microscopic theory. So if you follow those the frameworks, it's a little bit complicated. But instead, in this seminar, I try to discuss some more macroscopic framework. Because anyway, what we want to get is the low energy effective theory. That is macroscopic effective theory. So we can start with the thermodynamics instead of statistics. Okay, so we start with macroscopic theory. And actually, there's a very good method to determine the constitutive equation that is called entropy current analysis. So if you look up the very famous series of textbook by Landau in physics, you can find description of this method. Okay, so we start with thermodynamics. The first law of thermodynamics states the relation between energy density and entropy density. And the beta is the inverse temperature that is defined by derivative of entropy by energy density. So basically, beta is the thermodynamic conjugate quantity to the energy density. Or mathematically, it's Lagrange multipliers. This is the first law. And the second law states that entropy should be increasing function of temperature of time, shouldn't decrease. So in derivative form, it means the divergence of entropy current should be semi-positive. So this is the manifestation of second law. And this plays a very important role. So we compute the entropy current in this way. This is the zeroth order in derivative. That is just the entropy current appearing here times the flow velocity. So you can imagine some fluid cell moving with the velocity u mu. So this entropy is the entropy of one fluid cell. And also delta S mu nu is the derivative corrections. At this moment, we don't know the specific form of delta S mu nu, but we can determine delta S mu nu in the next slide. And you just apply this partial mu to those quantities, and you will get this form. So I just inserted this relation to replace partial epsilon by partial S. So here you have partial S, but here you have partial epsilon. Okay, so epsilon is again the energy density, which is conserved quantity. So in this way, you can have a relation between divergence of entropy current and the derivative of conserved charges. So this is the same equation. And now you want to make a connection between entropy and the constitutive equations. So at the zeroth order in derivative, the constitutive equation just looks like this. So when u mu is just less frame, then again, the theta mu nu looks like this diagonal matrix. But this is just generalization. If you have non-zero u mu, this diagonal matrix is converted in this way. Okay, so now if you have conservation law, you apply partial nu to theta mu nu that contains the partial epsilon. So you can insert this partial epsilon to here, and then you can combine the divergence of entropy with the constitutive equations. Okay, so if you insert this to here, you get this form. So it's a little bit more complicated, but actually there's nothing more than substitution. You just substitute this expression to here. Then you will get this one. So the first line is a leading order in derivative counting. And this term should vanish for any u mu. Because at ideal order or zeroth order, this is the equilibrium limit, so that there should be no entropy creation. So this gives you the relation this way. This is thermodynamic relation. And what is interesting is next to leading order. So you have this combination. And so here, beta mu is the inverse temperature times flow velocity. And theta 1 mu nu is a derivative correction to the constitutive equations. But at this moment, you don't know the tensor structure of theta mu nu. But you need to ensure that this term is semi-positive, because the thermodynamics tells you that this quantity, left-hand side, should be semi-positive for any configuration of T, beta and u mu. So you need to ensure that this term is semi-positive. That is made possible if you make a bilinear form. So if you make some unknown coefficient times square, then you can ensure the semi-positivity as long as this coefficient is semi-positive. Okay, so actually this is just a tensor decomposition. So this term is a trace part, and this is traceless symmetric part. So right, so this is just a decomposition, and if you have this combination, you can have a bilinear form for this factor and this factor. Then you can ensure the semi-positivity. And usually this coefficient is referred to bulk viscosity, and this coefficient is referred to shear viscosity. The physical meaning is that, so those quantity express how system behave when you apply the expansion or compression or shear deformation. So actually, the specific value of those coefficients depends on systems. So the all system-dependent information is encoded in those transport coefficients. But functional form is universal to any other systems that share the same symmetry.
Right. That's a very good
sure.
question. So you said this NLO in derivative should be semi-positive.
Yes.
Does it come from the stability of the fluid itself?
Yes, it comes from thermodynamic stability.
So if you change this sign, for example, by hand, then you get some instability in the fluid.
Right. Yes.
Okay.
It's not thermally stable if you have opposite sign. Okay, so what we did is based on the requirement from the thermodynamic laws, we constrain the possible tensor form of constitutive equations. So this is one famous derivation of hydrodynamic equations. Okay, now I'd like to move to the main topic, that is chiral magnetohydrodynamics. So I will discuss the renewed formulation of magnetohydrodynamics based on magnetic flux conservation, and also I introduced the chirality. Okay, so first of all, we need to identify the equation of motion. Again, we should have energy momentum conservation, and we can add some more conservation equations. The first one is the magnetic flux conservation. So F2 the mu is just a matrix which contains magnetic field and the electric field in some convenient way. So this is the high energy physics preferred notation of E and B, but this is just the usual electric field and magnetic field. So this equation gives you a conservation of magnetic flux. For example, if you look at zeroth component, you will get the divergence of B is equal to 0. So this is nothing but one of Maxwell equation that tell you the magnetic flux is conserved. So there's no end point of magnetic field. In contrast, if you look at Maxwell equation, the other half of Maxwell equation, you have E dot B, E dot E is equal to charge density. So this equation means there is end point of electric lines. So electric line is not the conserved quantity. So we will not include this equation as a fundamental equations. Okay, so MHD is based on the conservation of magnetic flux in this way. And the last one is the chiral charge conservation. So this is just a covariant, Lorentz covariant form of chiral anomaly that we discussed in the very beginning. Okay, so right-hand side is E dot B that we have seen in the previous slides. And CA is something called anomaly coefficient. So we will not worry about the details form of CA, but you can keep track of CA to see what will be an effect of chiral anomaly in the hydrodynamics. So just remember this notation, CA. Okay, so actually there is a seminar paper by Son and Slonka. So I would recommend you to look up D.D. Son's seminar in YouTube. So he is, he is very clearly explaining the effect of chiral anomaly in hydrodynamics. So here in this capture, he is discussing whether we could have a chirality separation if you put right-handed particle and the left-handed particle and steer the water. It's like you put the right-handed sugar and the left-handed sugar and steer the water and see whether you have a chirality separation. Okay, in case of sugar, I believe you wouldn't get the chirality separation, but surprisingly, the answer for the for particle physics is positive. Actually, he is explaining how he can get this chiral separation by rotating the fluid. So I just like to mention that the rotation or vorticity and the magnetic field is a similar thing. So there is analogy because both of them are given by rotation of some vector. So if you have chirality separation with rotation, you also have chirality separation in magnetic field. So and also another point is that actually the thermodynamic stability requires the chirality separation. The chirality separation is not only allowed by thermodynamics, but also required by thermodynamic stability. And those chirality separation or the current is called chiral magnetic effect or chiral vortical effect, depending on which field you have. So this is a manifestation of quantum effect in the fluid. So actually, those effects were discovered many years ago by high energy physicists and also condensed matter physicists. But more recently, the people in heavy ion collisions rediscovered those effects before 2010. And that triggered lots of experimental study in heavy ion collisions, and also it inspired condensed matter experiment. And those effect was confirmed by wireless emitters created by condensed matter physicists. Sorry, vortical effect is not confirmed. Magnetic effect has been confirmed with wireless emitters. So in this seminar, I'd like to further extend chiral hydrodynamics to the chiral magnetohydrodynamics. The difference is the following: is the paper by Sol and Soroka, they treated magnetic field as a kind of weak magnetic field at the derivative order, and also it was a static magnetic field or external magnetic field, meaning that it doesn't follow the equation motion. But in this extension, I'd like to basically there's no limit in the magnitude of magnetic field, and also I have a conservation equation of motion for magnetic field. So magnetic field is dynamical quantity in this extension. So the relevant variable in chiral MHD, magnetohydrodynamics, is energy density, fluid velocity, and a magnetic field, and axial charge. So axial charge is, remember, it's a difference between right-hand particle and left-hand particles. And also you can introduce the axial chemical potential, that is thermodynamic conjugate to the axial charge. So this is just the definition. Yeah.
I have a small question. Please go back. In order to include the non-conserved charge NA, so its explicit breaking is controlled by a small parameter.
Right, right.
So do you consider so what is a small parameter in this case?
Yeah, so in this case, anomaly coefficient is small. It also have H bar. So it's a small effect because it's a quantum effect.
So is it the reading order of H bar?
Sorry, let me say
So
again.
do you consider this effect is the reading order of H bar?
Yeah, so we take the H bar to be a small control parameter. So we combine the H bar counting and also derivative counting. So in combined expansion, this term is higher order. So zeroth order, we assume that JA is conserved quantity. And in the first order, next to reading order, we include anomaly effect. Okay, so I need to jump a little bit, but we basically follow the same strategy as the entropy current analysis. So here we have divergence of entropy current, but with more conserved quantities, conserved currents. So previously we only have this term, but now we have JA and also electric field, induced electric field. So we don't care about much details, but the point is that you can keep track of anomaly effect by CA. So this term is induced by chiral anomaly. And by making the bilinear form for this term, you can determine the constitutive equation for electric field. And further, using the Maxwell equation, you can get electric current in this form. That is given by anomaly coefficient and also electric field. So those two terms are usual ohmic current, but ohmic current is split into two components because in the presence of magnetic field, in general, you can have different value of ohmic conductivity in parallel to magnetic field and perpendicular to magnetic field. This is just a splitting. But the most interesting point is that you have the current proportional to magnetic field and anomaly coefficient. So there's no system-dependent coefficient here. So this term is completely fixed by anomaly coefficient. In contrast, ohmic conductivity depends on details of the system, what kind of interaction, what kind of particle you have in the system. But this term doesn't have such a system dependence. So you can compare the chiral magnetic effect and the usual ohmic current. You can find the difference in parity property because this is vector. The current is vector, so it's a parity odd, and the difference comes from the parity of electric field and magnetic field. The electric field is again the vector, which have parity odd, but magnetic field is axial vector, which have parity even. So that conductivity in magnetic field should be parity odd. And indeed, it is proportional to mu A, which changes sign if you substitute, if you exchange right hand and left hand. So the chiral magnetic field is induced only in parity breaking environment, where you have different number of right-handed and left-handed particles. So this is now called chiral magnetic effect. Okay, so finally, I tried to solve the chiral MHD equations. But the solving hydrodynamics is usually very tough problem in physics or even mathematics. The most difficulty comes from nonlinear coupling. So here nonlinear refers to those nonlinear terms with respect to the deviation from equilibrium state. Instead, what we are doing here is we decompose energy density from velocity magnetic field into equilibrium value and the small displacement from equilibrium. So we take those delta values to be a small quantity, and we only focus on the linear regime. Then you can actually solve the equation of motions by hand. That is a great simplification. So the problem is the following. So we have 6 degrees of freedom if you count it correctly. So you will get the 6 times 6 matrix equations for delta quantities. Okay, you can organize in this way because we only focus on linear terms. So then it is the the simple mathematical problem for diagonalization of this 6 times 6 matrix. Okay, and zeroth order in derivative, you have 6 waves. That is known as alpha wave and the magnetosonic waves. So alpha wave is a transverse wave. This is induced this is induced when magnetic field line behave as the usual string of guitars. So so magnetic field lines have tension. If you bend it, then you can have oscillation in this way. And also you can have sonic modes, that is sound mode. induced by real function of energy density and pressure. And the sound velocity have some modification due to magnetic field, because magnetic field also have some real functions. So that's why it's called magnetosonic waves. So we have 6 modes. And now we want to include effect of chiral magnetic effect, and we will find some helical excitations. Okay, the mathematical questions are again the same. So we want to diagonalize the 6 times 6 matrix. So that can be done if you solve the secular equations. That should be the 6th order in omega in energy. But actually you have cubic equation for omega square, because the waves in one direction is paired with the wave in opposite direction. So you should have a pair of solutions. So that's why you have a cubic equation for omega square. So that is much simpler than 6th order equation. And you can classify the solution for the cubic equation. And first of all, you have always one real solution in cubic equation, right? Because in minus infinity, you have minus infinity, but in plus infinity, you have plus infinity. So you should have one real solution at some point. So you can factorize one real solution, and what remains is just a quadratic equation. So this is classification of solutions. So diffusive mode refers to pure imaginary solution, and unstable mode refers to complex solutions. Okay, so depending on the direction of wave and also magnitude of mu A, actual chemical potential, you have different solutions in this way. So when mu A is small, you have 6 stable waves. That means you have real solutions. But as you increase the magnitude of mu A, you have unstable mode. You will get complex solutions. So we focus on those complex solutions. And without chirality, as I mentioned, we have 6 modes, that is the alpha wave, magnetosonic wave. And if you include derivative correction, that is basically dissipative effect. If you have viscosity, that is basically friction of fluid. So the wave should be damping. Okay, so this arrow means the velocity in this way, and also it's damping in time. But if you include chirality, the solution is completely changed. So how it's changed is following. So for example, you have 4 unstable mode and 2 stable mode. And what is interesting is those unstable mode. And you find that right-handed helicity is growing in this way. And in this pair of solution, again, right-handed is amplified, and the other is damped out, left-handed damped out. So this is the sign of imaginary part of solutions. So you have both plus and minus, and that corresponds to right-handed helicity and left-handed helicity. So only right-handed helicity it has an instability in this way, is amplified in this way. On the other hand, left-handed is damped in this way. So which of them is amplified depends on the initial sign of mu A. So in this case, when mu A is positive, the right-handed helicity is selectively amplified and left-handed is damped out. But if you change the sign of initial mu A, the role of R and L is interchanged. And in this case, left hand is growing this way. So finally, I'd like to speculate the origin of this unstable mode. Actually, it goes back to the chiral anomaly equation. And if you move E dot B to the left-hand side, you can organize the equation in this way. So it was actually no conservation equation for NA, but you can also look at as a conservation equation for some of those quantities. So the B dot A in the middle is called magnetic helicity. So initially we don't have magnetic helicity, but we only have chirality in fermion. But as the fluid is amplified, fluid velocity is amplified in the previous slide, you create actually magnetic helicity. And also maybe you can create fluid helicity as well. So here magnetic helicity and fluid helicity refers to the knots or linking of magnetic field lines or vorticity strings. So how this fermion chirality is converted to those helicity is an interesting open issue, I think. And that also determines the fate of unstable modes. And also, I'd like to just mention the similarity to the dynamo theory. So dynamo theory is known as the basic mechanism to create a magnetic field of Earth or some other planets. And yeah, go ahead.
Question. Is total characteristic composition? I have a question on the total characteristic composition. Is there the cross characteristic term?
You could have it. Yeah, you could have it, but maybe you need to make sure how charge conservation works. Charge conservation works. So all of them are charge conjugation even quantities, but cross helicity is charge conjugation odd. Okay, so this is the last slide. So I just mentioned the similarity to dynamo theory. And so actually this term corresponds to chiral magnetic effect. So this, yeah, so if you look at Maxwell equation with chiral magnetic effect, you have the same term. And this alpha corresponds to chiral magnetic conductivity. And also there's a similarity to non-Hermitian quantum mechanics that is studied in recent years. So this is our solution, and this is the solution from non-Hermitian quantum mechanics. The similarity is clear because if you linearize the equation of motion, that is just the first order differential equation in time and space. That has a similarity to the Schrödinger equation. So we can see the similar behavior. And we could study the topological structure in non-Hermitian systems. Okay, so finally, here I come to my summary. So in the first part, I discussed the formulation of chiral MHD that is based on the conservation of magnetic field lines. And also I introduced the chirality. And the last part, I discussed some topological phases of chiral MHD based on the solution of linear perturbations. And we find helical excitation if you look at the eigenvectors of solution. And the outlook is, of course, we want to see the fate of instability, the way we need to include a non-linearity. And also what will be configuration in the final state is an interesting question. That in the final state, you might have knots and link of magnetic field line and vorticity line. Okay, thank you for your attention.
Thank you very much. Very beautiful talk covering many topics from the basic things to the latest works. So it's now open for questions or comments from the from this room. Yes.
So for solving that your chiral MHD, you use that the entropy current method. So for example, to obtain that the relativistic viscous hydrodynamic equation, someone use that the different techniques like momentum expansion and so on. So do you think that what is the difference if you use that different
There's
method?
no difference at the first order level.
Yes, I think so.
But
yeah.
if you use the moment expansion, you can, moment expansion is not a derivative expansion, so you can automatically get the Israel-Stewart theory in that case.
And also, I think of topology, what you found is related to the order of the equations, or
Order of equations.
I mean, not
Yeah, so here I didn't include the dissipative effect. So if you include the dissipative effect, conversion from, so that implies you will get the another term for
another
dissipation.
term, yes, yeah.
So here I assume the ideal conversion from Na to magnetic helicity, but if you have dissipation, some part of chirality is gone due to the dissipation.
Or it's possible to obtain more complicated topology, or like
Due to dissipation.
yeah, the dissipation or more terms.
I don't think so. Dissipation
yeah.
is just a dissipation.
Okay,
Yeah.
okay.
Actually, more better understood in the absence of fluid mechanics. So yeah, so in the absence of fluid mechanics, it's just the Maxwell equation. And yeah, so if you solve Maxwell equation in the presence of chiral magnetic effect, you will get the helical magnetic field. But if you include ohmic current, that is another dissipation. That instability is reduced, diminished. So yeah, so basically dissipation just diminishes the effect of interesting effect.
Very much.
Any other questions? Can I ask a question? So in the last part, you talk about some interrelationship between chiral anomaly and fluid helicity.
Yes.
And actually, I couldn't understand well about the relationship between this magnetic helicity and the fluid helicity. Do you mean they are interrelated in dynamical way?
Yeah, I didn't mention it clearly. So this includes speculation.
This is speculation.
This includes speculation, but the speculation comes from the solution. So so those waves, the mixture of magnetic field disturbance and also fluid velocity disturbances. Because when you diagonalize the matrix, they are mixed with each other.
So that means magnetic chiral anomaly can create fluid helicity and vice versa.
Yeah, in principle, it should be possible.
And in your main talk, you looked only at the magnetic field part. This is the correct understanding.
We didn't capture helicity at the quantitative level. But we found is that if you look at the polarization, that is the eigenvector of the diagonalized matrix, we found it is the helicity eigenstate. So this implies that you should have a helicity in the final state of the hydrodynamic equation. So without chiral effect, it is known that those waves have linear polarization.
So that means you have to have simultaneously some result in the chiral anomaly effect by magnetic field and some fluid helicity the simultaneous way.
Yeah.
Okay.
Yeah, I think it's so without fluid dynamics, it's known as chiral plasma instability. But if you include fluid dynamics, I think you can have more interesting effects.
Okay, I see. Yeah. Any other questions? Is there a question from online? Okay. And can I ask another question, because there are many people from chemistry and biology in this room. But you have talked about the difference between left-handed particle and the right-handed particle. And actually, in the chemistry and the biology, we have many such particles or some molecules which has distinction between left-handed part one and right-handed one. And you said that some chiral separation effect can exist to separate the left-handed particle and the right-handed particle. And I was just curious if this kind of idea could be applied to the chemical molecule or biological molecule which has a left-handed side and a right-handed side. So I'd like to ask some question. What was actually essential to separate the left-handed one and right-handed one? In this case, you said the interaction between particles and the magnetic field is very important. And for example, do you have any suggestions for chemical compound to be separated for the left-handed part side and right-handed side by adding some external force?
Yeah, that is an interesting question, but we should first remember that the chiral magnetic effect or chiral vertical effect is proportional to anomaly coefficient. So it's an anomaly effect.
We should have some anomalous term
right.
in the chemical reaction, some other chemical interaction.
Right. So for example, in condensed matter physics, not molecules, it is not a free electron, but it is some quasi-particles. So in that case, if you have a similar setup as chiral anomaly, you have actually the chiral magnetic effect was confounded with wire separators. So in that sense, if you have something similar to chiral anomaly, you can have a similar effect.
So we need some signature to distinguish the left-handed molecule and the right-handed molecule by some external force.
Yeah.
Okay. Yeah, that's good. Okay, any other questions? So if not, so let's talk to the speaker again.
Thank you.
So we have lunch on the coffee room in the first floor.